Thanks for that, Brian. Good afternoon, everyone. Like you said, my name is Jose. I'm a Spark engineer at Cloudera. We've got a team of us who are focused just on the Apache Spark project, fixing things for customers, pushing fixes upstream. It's a good time. We're hiring, of course, so everybody's hiring. But I'm here to talk to you today about some lessons learned from production with regards to fault tolerance. So a little bit more about me. I have a joke. It's not much of a joke. It's a fact that a lot of other people on my team came down to the Spark stack. They were former application developers. They were former Spark writers for production jobs who wanted to dig into the internals. I came up to it. I have spent a long time at a previous employer working as a kernel and driver writer, so I have a sort of a different perspective with regards to how faults and execution and memory management work, and that's served me well so far working on the Spark project. So why do we care? Why does Cloudera spend any time talking about this? And it's because Cloudera is in the role of being a Hadoop supporter. We sell commercial support for Hadoop, and people run critical business logic applications on our Hadoop stack, on CDH, and we have to support them. And I don't know, I'm a retro video games geek, and I really enjoy Super Mario Bros. 3. So when I think big, and people keep throwing around big data, I think of the big world in Mario 3. You've got the big clouds, the big blocks, the big turtles, everything's big, 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 big. And specifically, we're talking about companies that make more than $1 billion a year. We're talking about, you may have seen some talks about scaling. We're talking about thousands of nodes in a cluster, thousands of hosts. And it turns out that outages at the scale are really expensive. So I'm also an aviation geek, and I just did a fun back-of-the-envelope calculation. So maybe you're familiar with Amazon EC2. And it turns out that if you've got 1,000 M4 4 extra large cluster nodes allocated to yourself, and you just have them sitting there doing nothing, it costs about $1,000 an hour. So I looked around, and I found that the Phenom jet, which has about 6 seats, 2 jets, two little turbines in the back, just flying around empty is about $1,000 an hour. So for every minute of downtime that your cluster's got that is not doing something valuable, it's like flying around an empty airplane. This is completely apart from the fact that you've got some critical business application that's not running. So we care about it pretty deeply. So what we're going to do is we're going to talk about one particular issue that we at Cloudera fixed. We're going to talk about one bug. We're going to talk about what happened and how we fixed it. Let me preface this first by saying, please, Spark is extremely fault tolerant. It builds on top of MapReduce. A lot of people care about this. I'm in the world where when we talk about fault tolerance, we're talking about some particular edge case. So we're in this unique position where we tend to see bugs on 2,000 node clusters before a lot of other people do. And when we see these bugs, we fix them. So we're going to talk about one of those bugs. But again, let's just do a quick recap on fault tolerance. So this is a diagram that I stole from offf.com, just showing how a shuffle works. So the way that Spark works, as you've seen countless times through this summit so far, is your job, your Spark code, is broken down into stages and tasks. Your data is broken down into RDDs, things execute in parallel. If you take away nothing else from this graph, just realize that it's a graph. That's all that really matters here. One of the keys to the fault tolerance model in Spark is this idea of lineage. So when something happens and you lose some piece of executed data, you don't necessarily have a backup of it. It's not like MapReduce where you're checkpointing to disk every single time. You're checkpointing occasionally, sure. But in many cases, Spark itself is going to recompute a lost piece of data. The bug that we'll look at is a particular failure in recomputing. It's another sort of quip from aviation is that it's never 1 or 2 things that go wrong. We can deal with that. It's always 3 or 4 things that go wrong. So we're going to talk about 3 or 4 things going wrong. So again, this is a pretty classic Spark execution diagram. What's happening here is you have an RDD that's being mapped to another RDD in stage 1. Between stage 1 and stage 2, there's a shuffle operation, and then there's another map operation. Sure. So we've talked about RDDs and we've talked about lineage. We're going to be focusing again on Spark itself. So Spark builds on top of other layers such as HDFS that have their own ways of dealing with fault tolerance. So specifically, HDFS does this trick where every bit is backed up in multiple places. Generally, you've got a master copy, you've got a second copy that's local, and you've got a third copy that's distal, it's far away. Or maybe it's HDFS and Spark together taking care of that. And HDFS itself also has, oops. Yeah, it's got multiple masters. We're not talking about HDFS itself. Also, Yarn itself will have some fault tolerance built in. We'll talk about that a little later. We're specifically going to be talking about the scheduler within Spark. The scheduler is a very important piece of code that takes your job and takes the output of some graph processing that's broken down your job into these tasks and stages and figures out, okay, where are we going to perform this work? Where are we going to perform this actual execution? What executors, what resources that can perform computation are going to do this work? So we'll be talking about the scheduler, and in particular, we'll be talking about a blacklist mechanism. So this is a new slide. This is the little experiment I'm running. I'm also a cooking geek. And some of you are from New York. You know, we're in Boston, so New York's not too far away. Maybe you're familiar with Junior's restaurant on Flatbush Avenue in Brooklyn. I grew up in Brooklyn, and I love the cheesecake there. I love it so much that I got the recipe online, and I made it. And it was terrible because the recipe was completely out of order. It was not optimized. So I decided, hey, what would I want to do if I had multiple people helping me in the kitchen? Or what would I do differently if I was trying to make 1,000 cheesecakes? So I took the entire recipe itself, and I mapped out its dependencies. I executed the entire recipe as a set of state diagrams. So this is, the reason I have this up here is because this is basically what Spark is doing behind the scenes to your Spark code, to your jobs. And in terms of fault tolerance, let's see if we've got a little laser pointer. Ooh, laser, great. Well, let's see what happens if we drop this bowl on the ground right here. We have to recompute. But we don't have a backup of what happens at this step, but we have the lineage. So we go through the graph, and we perform all these steps again until we are able to recreate that step. And maybe, just maybe, if we drop that bowl on the ground 3 or 4 times, we're going to give up for the day. Maybe we've got butterfingers. We don't want to do this recipe anymore. This may seem like a little bit of a stretch, but in fact, this is exactly the bug that we fixed, in a sense. So if you take away nothing from this graph, it's just that here's a job, here are a bunch of dependencies, it's a graph, and just like Spark, we can recompute just a part of it. And another food service analogy, things are just a little different in production at scale. Again, on 2,000 node clusters, we tend to see things that other people don't. So this is just a picture of, it's actually my boss at Cloudera, who is a hobby barbecue chef. He and his family go to barbecue competitions. So me cooking one piece of meat in my backyard is very different from making hundreds of them for a big audience. All right. So I think we've got just enough background now that we can really take a look at the main part of this presentation. We're going to look at Spark 8425, which is an application outage. It's a JIRA that we at Cloudera logged some time ago. Well, no, it's not true. It started out as a blacklist mechanism bug, but we at Cloudera have worked quite hard to make some updates to it. Okay. So let's start the story at the very beginning, April 22nd of 2016. We have a number of customers. One of these customers is one of the 3 largest banks in the US. And this customer was very upset, really, really quite upset, because they had some critical job that ran in a Spark cluster that has to return an answer within 7 seconds or else the world ends. And that job failed. It stopped running. It had been running for days. It had been moved from production cluster to production cluster. It was pretty well working. They'd built a whole bunch of business logic on it. Now it's not working. Your plane, your fully loaded airplane is now flying in the wrong direction. You're just burning money every minute. You're losing opportunity cost every minute. This was running on a customer's cluster, hundreds of nodes, hundreds, not thousands, but high hundreds, so pretty well up there, 8 disks per node, and presumably many CPUs, many gigabytes of memory, pretty decently sized cluster. And there's a pretty reasonable expectation of high availability from this thing. And now let's just take a pause for a minute and recall that Spark clusters generally are running on commodity hardware, much like the MapReduce clusters that came before them. And commodity hardware means you don't necessarily have RAIDs on your individual nodes. You don't necessarily have multiple power supplies. You don't necessarily have error-correcting memory or any of these other things that take care of fault tolerance at lower levels. In fact, you're exposing all of the fault tolerance to a higher level of the stack. And that's a key thing here, that if this were running on a rated node, maybe we wouldn't have seen this failure at all. So again, it's always multiple things that go wrong, but we do end up exposing a concrete failure. Sure. So the customer is very upset. Cloudera support, of course, is excellent, and key plug for Cloudera there, by Cloudera. So we get on the phone with the customer. We're able to get their cluster running probably in about 2 hours, and we're able to give them some workarounds that I'll talk about in the next slide. But after looking through the log files, after thinking about what's going on, the immediate cause of the failure was a file not found exception. This should be something that's caught. This is a pretty concrete thing. So, okay, we start digging. It turns out, I'll read this quote on the bottom. HDFS and Yarn responded to the disk failure appropriately, but Spark continued to access the failed disk. So let's reiterate, oh, not that slide yet. So let's reiterate exactly what's going on here. We have multiple layers of software. We have HDFS, which has its own mechanism for recovering lost files, meaning it keeps multiple copies of them. We have Yarn, which is able, in its own way, to recover from errors. And we'll talk a little bit more about the interaction between Spark and Yarn later on. But for now, Yarn was able to see the failure and deal with it. Not in enough time. In some cases, it's possible that Yarn would have caught this before Spark did. But Spark continued to access the failed disk. And what happens when it accesses a failed disk repeatedly? Okay, so we look into this some more. One node has one bad disk. Again, hundreds of nodes, hundreds of disks, one node, one bad disk. But this is where the scheduler gets us into a bind. So when the executor that's performing some chunk of execution is running on a node, on a host with a bad disk, it will fail. It will either fail because it times out, or it will fail, as it did in this case, because it can't find a file. Because I'm talking about an actual hardware corrupt disk here. The disk itself is failing. We've had a head crash, there's a bad sector. It's just getting worse and worse and worse. So we observed that tasks succeed if they schedule on other nodes, and tasks fail if they schedule on the same node. Okay? So the scheduler will eventually kill the whole job after some number of failures. So we get into this sort of pathological edge case. Spark is fault tolerant, but it also tries to be performant. So when something fails, and when we have to recompute it, the Spark scheduler will look around, and it will make it'll make its scheduling decision based on a few things. One, well, let's look around to see where there might be a node that has some capacity. Oh, look, there's this node right in front of us, and it just had an executor fail early. The executor is stopped. We don't know why it stopped, but it stopped. He's got a bunch of extra capacity, so let's schedule there. It also makes a decision based on data locality, and oh, look, there's this node right in front of us. Not only does it have some extra bandwidth, but it also has the data that we needed, and we sort of don't realize at this point the whole reason that it's got some spare capacity and it's got this local data is because the job just failed. So we pathologically try to reschedule the same job in the same place over and over again. And eventually, in this configuration of Spark, we will hit a maximum number of retries, and the whole job will just fail. Well, what happened? Spark is supposed to be great with exactly this, and this is what we think is a pretty trivial issue. Again, multiple things going wrong, and we hit this one particular issue that kills the application. So then, let's come back earlier. Spark depends on Yarn to tell it what resources are available. Or Mesos or your standalone or whatever your cluster manager is. I'll say Yarn because that's sort of what I'm used to seeing Spark run on, but in your head substitute Mesos if that's what you use. And Yarn is responsible for telling Spark, hey, I've got this many nodes, I've got this many executors, here's what I've got. Yarn itself is capable of performing its own checks, and in fact it does. It has something called a disk check. It'll try to write a file to disk periodically, and if it fails, it'll flag a particular node as having had a disk failure, and it'll take it down. However, two things. One, as configured in this cluster, that service was only running maybe every minute or so. And all of these failures that we saw in the scheduler happened between the span of 2 health checks. After the job failed, pretty soon after that, Yarn picked up on the fact that this was a bad disk. Another thing, too, is we say, OK, well, Spark knows that a job has failed. Spark maybe can even see a file not found exception. Why don't we give that to Yarn? And the trouble is that there's a trust boundary there. Yarn is just a dumb resource manager. It's relatively policy-free. There's not really any way of authenticating with Yarn and saying, hey, this is something that we trust. Any mechanism that Spark could use to tell Yarn, hey, this is blacklisted, don't use it, is also a potential DOS vector. We've talked, there have been a few talks at the summit here today about using Spark as a shared resource. Maybe you're a university or something and you've got some cluster that you're giving to lots of people. You don't want someone's, not even malicious code, let's just say naive code, telling the cluster manager, hey, all the resources are bad. You don't want to be failing other people's jobs. So this is sort of the world that we have to play in. So let's just recap the failure for a moment. Again, there is already fault tolerance in Spark, and it's really quite good. I mean, we see Spark recover from all sorts of issues in production all the time. And I want to reiterate, please don't be worried about Spark's fault tolerance. Really, the tone of this talk is sometimes we find some really interesting edge cases that make us want to improve Spark, and this is an improvement that we made. So again, here's the recap. Spark can handle a single unreachable node. If the whole node catches fire, if somebody pulls a plug, it won't respond to pings, we won't schedule on it. Great. We can handle a node with no usable disks at all. If we can't even allocate resources on it to start with, it's great. What happens is this one particular case where sometimes a disk fails and sometimes a file to be read will trigger this whole cascading failure. So really the way that I like to phrase our root cause is the failure modes are binary. They're not expressive enough. We need to add a language. We need to add some way of making the failure modes less binary. We need to add more mechanisms for retrying. We need to improve the granularity of our failures. You've heard some talk earlier at the summit about decreasing the granularity for execution, and that's all great. But when it comes to failures themselves, we want the scheduler to be able to make more intelligent decisions about what to do. And this is what I said when we discovered all of this. This is not great. Okay, so right away, what do we tell the customer? We did not tell the customer to do anything with Spark speculation. What we did is we had them set 2 keys. One of them is this executor task blacklist time, which is a hint to the scheduler, at least as of Spark 1.6 when we were fixing this, how long a particular executor should be blacklisted when it fails. So for example, if your individual tasks are all taking about 2 minutes, let's blacklist something for much longer than 2 minutes. If you only blacklist something for 30 seconds or so, there's a chance that you'll re-execute on it. And the hope here is that this is just a condition to delay the scheduler so it doesn't hit this failing resource again. We also set this maximum failures for a whole task to be a higher number just to have Spark keep retrying. This was enough to get the cluster back up. This is not a general solution. Here's the general solution. Let me stress, and this is something that from my kernel development background is pretty familiar to me. The scheduler is a key part of the execution engine. It has to be right. It has to be right in a lot of different situations. It has to be correct when you've only got 1 node. It has to be correct when you've got 2,000 nodes. It has to be correct when your job has very, very few stages. It has to be correct when your job has lots of stages. It has to continue to persevere and continue to attempt execution when your correctly crafted job fails for a hardware reason. And it also has to fail extremely quickly when a naive user runs an application that simply fails immediately. Let's say it divides by 0. We don't want to try to divide by 0 on every single executor on every single node in the whole cluster. It's, again, you're flying your airplane empty. And it has to be right. So it's sort of a game of whack-a-mole. The point of this here, this slide, it's a little bit of an eye chart, but really what I want to do is to drive home the fact that We really had to think through a number of cases here. If you're curious at all, pull up the Blacklist tracker in OAS Scheduler. It's all of our changes are now checked in, and I believe it'll be part of Spark 2.2. The last change just went in, maybe in the last week. And by ours, let me reiterate, at Cloudera we have a team of dedicated Spark engineers. We've got 2 committers who are on the Spark team itself, who work pretty actively, Imran Rashid and Marcelo Vanzen. And they and I and the rest of the Spark team have been working on this for some time. So here is our final improvement. We've added a few different configuration variables to Spark. What we did is we started with the existing blacklisting mechanism. Prior to our work, there was some code within the scheduler to notice when certain execution resources have failed and blacklist them, meaning mark them as persona non grata, mark them as unusable. We took that and we really took it to the next level. So these 4 configuration keys allow a finer grained description of failures. We've got task attempts per executor, task attempts per node, which is how many times we retry before we give up. Max failed tasks per executor, max failed task per node is, again, the maximum number of times that something can fail. And that's it. These are the default configuration values. You'll have to enable the blacklist in Spark 2.2 or whatever, but if you are running a large cluster, this is something that Cloudera support would recommend doing. Let's take a quick look at the UI part of this. So this is one thing that I worked on, and a couple of changes to your normal Spark executors web UI here. Now we have a new column that says blacklisted. When we look at our executors, we can look at the number of active executors that are blacklisted. Active and blacklisted is a new state. If we go down to the whole list of executors down here, we can see that executors 0 and 2 are blacklisted. Another point for reliability, I don't really have a great diagram for this one, is sometimes, depending on your configuration, when a particular executor fails on a particular host, maybe we want to just kill that executor. In fact, maybe we want to take down the entire host, because outside of this, we have a system administrator, a physical human being coming in and doing something. Now, when a node is blacklisted, when an executor is blacklisted, it'll send out a logging event, and certainly you can configure your cluster however you want. Maybe you've configured your cluster to look for this particular blacklisted task or blacklisted executor message and perform some action, like notifying somebody. But in some cases, the web UI may not even reflect blacklisting at all because it'll simply kill things. So you have the choice of either keeping around blacklisted resources and maybe waiting 5 minutes or so until they restart. There's a configurable timeout time, or just kill them. Okay, so that's the blacklist. Now, I want to talk about Spark 4105 very briefly here. This isn't just to talk about blacklisting, it's to talk about fault tolerance. And not all of Spark's fault tolerance issues are necessarily in the scheduler itself. They're certainly in core code, but they're not necessarily in the scheduler. So let's talk very briefly about these shuffle fetch failures. So let's go back to our lovely diagram here, this lovely DAG of the shuffle fetch. And let's say that one of these things right here fails, one of these orange arrows. And what this represents is a shuffle. It means it's a many-to-many mapping between one stage of computation and the other. It just means that a lot of data is being passed around the cluster. Occasionally, and non-deterministically in a way that's really difficult to reproduce, you get this failed to uncompress error. Some piece of shuffle data comes in and it's unusable. And it seems like stream corruption. I've chatted with some engineers who propose that it could be a TCP issue. We actually don't have this root caused at all. But again, it was causing a sort of file not found exception, or actually an IO exception. So the patch for this is just to retry it. Not too exciting, but at least it prevents failures. We haven't spent 6 months working on this one, but this is enough to unblock a customer. It's one that we've certainly hit a number of times at Cloudera. And it's fixed in, it's fixed in Spark 2.2 if I understand correctly. Okay. So I do want to leave a little bit of time for questions at the end. So let's go to some closing thoughts. What did we learn? So the Spark scheduler is responsible for assigning units of work to compute resources. Maybe if this is your first time diving deep into the sausage factory, into what happens behind the scenes, When you take your job, it's translated into a DAG. That DAG is translated into executable units, and something has to actually go and execute those things on your cluster. It's really where the rubber meets the road when it comes to fault tolerance. And there are a few knobs to tweak, and there are other things that can fail, but generally, when you have this sort of task failure, that's the sort of place that we're going to start looking for bugs. And one takeaway from my point of view is that Spark is a distributed system. There's a pretty rich literature describing distributed systems going back 20, 30, 40 years at this point. And Spark does an excellent job of either masking or fixing or abstracting away many of the issues with distributed systems. I mean, it's just so easy to run a Spark job on a 1,000-node cluster. But the issues are still there. So it can be very helpful to look at prior art when it comes to these sorts of issues. And I'll leave you with one thought, a recommendation for application developers. So really, when you are growing your job to run on a 2,000-node cluster, don't start with that cluster. When you're learning to fly a plane, don't just hop into the twin-engine jet that you want to fly in. Build it slow. Make sure you understand every stage of the way. Make sure you set expectations. At least for me, when I'm running these jobs, it's helpful to sort of have a scientific method when I go from 1 node to 2 nodes to 5 nodes. Make sure that I'm seeing scaling the same way. And also see errors. If I see an error as a Cloudera partner, for example, on a 2-node cluster, that's much easier to reproduce and to fix than on a 1,000-node cluster. So grow organically. I mean, it's pretty obvious advice, but it certainly helps here. All right, so with that, we've got a couple of minutes for questions. Thank you so much. And I hope you leave feeling that Spark is super fault tolerant, because it is. Thank you.
Hi, thank you. The great talk.
Thank you.
How do you simulate failures when you develop this stuff?
How do I simulate failures when I develop this stuff? So one thing we do at Cloudera is we have all sorts of internal testing. The Spark project itself has unit tests, which we'll run. And if you, as a Spark contributor, go and run something, you're encouraged to run the unit tests locally. The AMP Lab will run them. At Cloudera, we have a mechanism for creating clusters. We have some automatic deploy scripts that will generate EC2 or GEC clusters with as many nodes as we want. And we also have a team that works specifically on sort of a fault injection framework. We've got a framework that can simulate a bad or failed or slow or inconsistent disk or network or CPU or corrupt memory. And we sort of have a QA team that works on that. Now, this particular issue came from production. So fortunately, it's not our $1,000 an hour finding the bug, it's the customer's. But it also means that we need to fix it that much faster. So we both do internal testing, and we run health checks on our customers' clusters.
So I wanted to ask, how does this play with dynamic allocation of executors?
It plays pretty well. So the question was, how does it interact with dynamic allocation? Dynamic allocation is sort of orthogonal to this. Dynamic allocation just means that we'll create and destroy executors along the way based on demand. If either the cluster manager or Spark, I think it's generally the cluster, well, either one, sees that we have too many or not enough resources, it'll make different decisions. This is just another thing that can destroy executors. So ideally, your cluster manager or Spark would know not to allocate things on there. So because we have this blacklist, let's say at noon, host number 22 is put on a blacklist for an hour. And then the amount of load on our cluster drops and we kill a bunch of executors. And then at 12:30, we have a huge burst of work coming in. We're trying to allocate a whole bunch more executors. Host 22 is still on that blacklist, so we won't try to create any resources on it. And ideally, some system administrator has come along and is looking at host 22 and trying to figure out why it was taken down. So, I mean, they're orthogonal. They don't work super closely. They don't really get in each other's way. But it's, ideally, you're not trying to reallocate.
So this is just a clarifying question. You talked about the settings for max number of failures per executor as well as max number of failures per node. in this context, when you say node, are you referring to a host or
Yeah,
a Yarn container?
I've been sort of sloppy with that, but yeah, node and host specifically refer to one system. One host name, one machine, one container that can run executors. And that's, I think generally within Spark we refer to nodes. The Spark scheduler code refers to nodes, but one and the same, not anything Yarn related. Everything Yarn specific is outside the scope of this talk.
And that's all the time we have for questions. The next talk begins at 3:20. Thank you, Jose, for this talk.
Thank you.